No, she already said that. I was just thinking about that.
So I've taken my. Oh, wow.
Lynn said, "Take some time to be able to." What? I hate what you know. It starts to make her.
We have more. I was thinking like. Oh.
Very small.
See, the thing that's why. So I remember I got my.
So Monday that's class, Wednesday the reading.
I did this in a while, so. I bought some room. It's so serious. Property tax.
No, we're both the sixth.
Items, but. It gives, it was that.
Like, you know, name like that. I look at it, two-page like background. I with my friends, because I was out on all of my friends, and
Already.
oh, I think.
Okay, good afternoon, everybody. Last class. I'll give my usual thank you spiel at the end. I have a couple of announcements before I jump into the notes. The first one I want to say is this is my annual one time I'll remind you and humbly request that you fill out your feedback for me for my course student evaluations. Really, really important to me in particular. I say this every semester. Every change I make in this class is due to a suggestion by one of you. I don't take suggestions from anybody else besides my own ego and you guys, mostly you guys. You might notice that you may have suggested changes in the past. Again, I have to filter things to think about what's appropriate for this course. But everything that I've done over the last 3 years, all the changes I've made to content, to grades, to problem sets, to difficulty, everything's because of you guys. Please fill it out. I can't, as I always say, I can't give you any incentives for doing it. However, I will say that the university has announced that the department that gets the most feedback from students in terms of percentage gets a pizza party. So subs, you guys don't get that pizza, I get it, so please fill it out because I want free subs. I'm looking for, usually I get about 60% of you to fill out, which is actually really, really good. The average at the school is like 45 or 40%. So you guys do pretty good. You're like a standard deviation above on average for me. I'd love another standard deviation on that because I want some pizza. I think they're due at the end of classes, right? Thursday, Tuesday, I think, or something like that. So please do. I read every single one of them. I save the PDFs of all my evaluations that go into my portfolio. I actually read every comment. So negative, positive, neutral, it doesn't matter to me. I like them all. The next thing I wanted to say, I made an announcement on all your lab canvases. There's a notebook check. I totally forgot that I need to do it. So I put a box outside of lab. I think it's a mailroom box. It's on the ice maker. Just drop your lab notebook off by Tuesday. I'm going to grade them all myself in just one go. Return grades, and I'll put them back in the box, make an announcement, and come pick them up. Okay, it should be Wednesday or Thursday at the latest. Maybe Friday. We'll see. Anyway, I'll get them done really quickly. It's only worth like a pre-lab equivalent. I think it's just a couple % of your grades, not really a big deal. So I already got an email from someone that says they threw theirs away. Which is unfortunate, but it's not a terrible penalty. And you can just send them in and I'll check them off for you. Last thing is the last assignment's been posted. You have looked at it. It looks scary. I think it's 12 pages, but it's mostly, hold on a second. It's just mostly writing. It's like, as in one of the problems, let me just show you in particular. I'll just walk through it really quickly. And again, you're free to come to me. We'll have extended office hours next week, Sean and I both. Once labs end. We returned, one of the questions is a follow-up to that spin 3 halves question on the homework. It has to do with molecular orbitals. This Huckel problem is literally, you use this calculator. I give a link to it. It's on the Canvas announcement page as well. You build a little molecule asking, it tells you what the molecular orbitals are, the energies and stuff. Basically just using the calculator and answering some questions about the result. No math, you have to do a little bit of math in this problem. At the end, I asked you to calculate some enthalpies and some energies, just arithmetic, thermodynamics, not too difficult. The quinone problem is a linear regression problem. Literally just two very simple linear regression problem and just a little bit of qualitative analysis of it. Plugging in some values into your linear model. Shouldn't take you that long to do. And then the final problem is, it has a lot of writing, but it's basically I'm introducing a technique to you, explaining how it works and how we can use it to measure the molecular orbital structure of molecules and explain how molecules change as we remove electrons from orbitals. So this question actually goes through a lot of pages of discussion. It uses water as an example. I talk about how to do the analysis on the water spectrum and what it tells us. And then I ask you a really, really simple set of 2 questions about hydrogen bromide. Very little math, actually no math at all. Draw a little molecular orbital diagram and then explain the spectrum. Right? I wrote the problem. Now, it's not really fair to compare how long it takes me to do a solution set to how difficult it is, because again, I write the problem sets. But the bigger problem sets, the ones with a lot of calculations, they tend to take me a couple of hours to do the solution sets. This took me 15 minutes. Okay, so it's mostly qualitative. It's not too hard. It just looks bad, but it's not bad. Hopefully you'll find it interesting. Anyway, we'll make announcements about office hours next week. I just need to talk to Sean one more.
Do you know if Sean's having his office hours today?
He is. Sean will be here today. And in fact, I think we're going to set it up so your exam period in this room, which I think is next Friday, the assignment for the exam period for this room, I think is next Friday. I have to double check that. We'll be in this room, right? So we'll hold office hours in here for the homework during the exam period. Anyway, I'll make an announcement about all of that.
And then this is the final exam.
This is it.
Okay.
This is it. Turn this in and it's done. You're no more work. Simple as that. And it's just a normal, just think of it as a homework assignment that's worth double.
All right.
That's it. Nothing different. Okay. Let's finish on molecules. Unfortunately, I don't have that. So 2 things. I'm going to try to get through much about molecular orbitals today. It's not, it should be enough. You should be comfortable with the homework at this point after today. I do have another lecture on Monday, the other section. I'm going to talk a little bit more about polyatomic molecule system. I'll record it. I will upload it for you guys, the notes, everything. You don't need it, but if you want, it might provide a little clarity from the homework. If you want it, you can use it as a resource, but it's not required material. I tried to make the problem set as easy to approach with just the material that we've talked about today. But the other section, because of a few things, there's ahead by about a half of a lecture or 2/3 of a lecture. Just a little behind here. Okay, so let's go back to where we were beginning last class. Forgive me, I'm a little distracted today. It's been kind of a rough week for us academics. So we were looking at, we moved away from hydrogen, which again, only two 1s orbitals combined together to make a molecule. Very simple, 2 electrons, not too hard. Nitrogen, we've got a little more complexity, right? We have we have p orbitals now. We have multiple, we have a core and a valence. We have to think about how the presence of these electrons affects the bonding of our molecule. And so I'll just kind of roughly go through what we talked about at the end of last class. This is the last slide for my presentation on Tuesday. And the idea is, again, we have to take into account very simple rules about molecular orbitals. And these work very well for 99% of cases in chemistry. There are exceptions, of course, as there always are. That valence electrons determine bonding, core electrons do not. We'll see that. In fact, we already did see it. Like the 1s electrons in nitrogen, they're very, 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 very deep towards the nucleus, because the nucleus has 7 protons in it, lots of positive charge. The core electrons are very attracted to that, so they have a lot of attractive potential energy. So if you think about the energy of relative to ionization, this is saying that it takes 100 eV to remove that electron. Remember, the EV is about 90 kilojoules per mole. So these are 9,000 kilojoules per mole away from ionization. Very, very deep electrons. Right? And so when they combine, the only thing 1s combines to a nitrogen is 1s on the other nitrogen, because they're the only orbitals that deep. And what happens is, again, you form a bonding anti-bonding pair between the 1s orbitals, just like you do in hydrogen. But we have 4 electrons in total, 2 for each. Right? They're fully filled valences, fully filled cores. And so the bonding and the anti-bonding pair are both filled when they form the MOs, and therefore there's no net bonding. Right? The bonding and the anti-bonding cancel out. Right? This is why core electrons don't participate. Because there's the atomic orbitals are fully filled, so when you form the molecular orbitals from them, all the antibonding orbitals are filled up. No net bonding here. Right? So we don't really care about them so much. I mean, there is a strong connection between those 1s electrons, and they're interacting very, very strongly with each other, but it doesn't affect the bonding at all. Right? The actual overall interaction. We basically cancel each other out. Okay, so now we go to the valence, the N equals 2 of nitrogen. We have S's and P's. The S's are closer to hydrogen, or hydrogen's S orbitals are 13.6 eV. So this says that they're a little deeper. And that's, of course, because these 1s electrons shield the nucleus, but they don't shield it completely. These are a little deeper because they feel a slightly more positive charge from the nucleus than just +1. And so 2s here, 2s and 2s combined, they're fully filled, they cancel each other out. Right, so we're just left with the 2 p's. Right, and that's not surprising that we're left with the 2 p's because they're the ones that are unfilled. Right, in atomic nitrogen, each of the p orbitals have exactly 1 electron, 2p3. So these electrons ultimately determine bonding. Right, we're combining hopefully 3 p orbitals together with another set of 3 p orbitals to form 6 new molecular bonds, or sorry, 3 new molecular orbitals, excuse me. New molecular orbitals. And they're only half filled, right? So if there are 6 new orbitals that are formed, each fills 2 electrons. We have 6 electrons. That means the molecular orbitals are going to be half filled. Right? They're not going to cancel each other out. So the p orbitals ultimately determine the bonding in nitrogen. And so we looked at, again, we have to consider geometry because p orbitals are directional. Right? They're not spheres, they have directions. There's an x, there's a y, and there's a z component. And we have to consider the geometry when we combine atomic orbitals together. And thankfully, p orbitals are pretty straightforward. They're orthogonal to each other. The x doesn't interact with the y doesn't interact with the x, and they don't interact with the z. They're all interacting separately. So only like interacts with like, right? And we form 3 different bonding anti-bonding combinations of p orbitals. We have these 2 that are called pi orbitals, right? P-like orbitals. They have this kind of, I don't know what I'm going to call it, donut-like shape around the bond. Right? Where there's no probability of the electrons being in the bond, but rather above and below the bond. They're called pi orbitals, and those form from the combinations of the x's and the y's. And then we have the z orbitals, which lie through the bond, right? And they can interact like s orbitals, right? They interact through the bond in a spherically or cylindrically symmetric way. Through the bond, all these s-like or sigma orbitals. And so we have these nice bonding, anti-bonding combinations from the p's. Okay, so we form, right? We take in 3 times 2 atomic orbitals, right? We have 3 from each. We get 6 molecular orbitals out, right? Number of AOs in, number of MOs out. We get a bonding, anti-bonding pair for each of these 6 total. Right? And they all bond constructively. Right? Just draw. They look like they bond nicely. All right, we don't know how effective this bonding is, right? So for instance, is this a stronger bond than this one? Right? It's kind of hard to determine that just qualitatively, right? Which one is more bonding than the other? And it turns out that's a complicated answer. But there's a trend, and it has to do with the periodicity of the second row. As you fill the valence, the bonding characteristic of the s relative to the sigma relative to the pi changes. Right? So I want to show you that trend today. How we rationalize which one is stronger than the other. And it turns out, again, it comes to shielding, right? The core electrons shield the valence electrons, right? And change the energies of the valence electrons. And as we change the energies of the valence electrons, we get different bonding interactions. And so as we add more valence electrons, that affects things. And we'll see that that these bonding characteristics between the the pi's and the sigmas change. So what I want to do initially is to take all this data together and draw a molecular orbital diagram for N2. All right, which we've kind of done casually here, but let's do it for real. Let's make a nice little diagram. Put all this information together. So again, our molecular orbital diagram, let's do a nice big one. Typically is measured, we measure it along energy along this axis increasing. And we always, and in my case, I always like to set the energy equal to 0 as the ionization limit. So everything is negative. Right? This is the ionization limit. How much energy it takes to remove an electron. Right? So everything's going to be relative to this limit. Everything's going to be negative if the electrons are bound. Right? And I already wrote down all the energies. So I'll just kind of redraw what I have on the previous slide. Right? We start with the 1s's, right? We have a 1s2. And again, I'm going to write this like on the left side, I'll write one atom. On the right side, I'll write the other atom, Na and Nb. And in the middle, I'll draw the molecular orbitals for N2. Okay, so on the left-hand side, I introduce a 1s orbital and another 1s orbital. These are at around minus 100 eV in energy. They're very, very deep. There are 2 electrons in each of them. And we know how sigma s's combine. They combine into a bonding and anti-bonding pair. So this is a sigma bond. Right, this is the sigma bonding orbital down here, molecular orbital. And then we usually call the anti-bonding, we add a star. Right, so this little star means anti-bonding. So we have a sigma and a sigma star. And we fill these completely. Right, so the 1s doesn't contribute at all to the bonding because there's equal amount of anti-bonding and bonding character for this interaction. There's no net bonding. Okay. Now what I'm going to have to do is we have a big gap between 1s and the next orbital because of shielding. So I'm just going to put little dashes in here. You don't have to do this, just to say that, hey, we got to go way up in energy before we get to the next set of levels. And so we're left now with 2s2. Right? And of course, these are both completely filled. Nitrogen. And of course, these are at, what did I say? These were at 18 eV. And we get a nice set of bonding and anti-bonding sigma orbitals. And they're completely filled because, again, we have 4 electrons in these orbitals. Okay. All right, so that's all straightforward. Now we have to do the P's. All right, and remember the X's and the Y's interact identically to each other. They both form pi orbitals in the exact same way. One's along the y-axis, one's along the z-axis. So just rotated 90 degrees. So the bonding interactions and anti-bonding interactions of both are equivalent. They're just on different axes. The problem is that we can't tell necessarily whether the z, right, the sigma bonding with the pi, with the p orbitals, is stronger than it is for the pi orbitals. So unfortunately, you have to appeal either to calculations or experiment to determine this. Let's go ahead and just set up the problem really quickly, and then we'll come back to this, right? So we have 2p3. Let me just put this a little higher up in here. Have some room. Right, so we have a 2p3. I'm going to actually draw it a little differently. I'm going to put the z here and 2 x's. Even though they're the same energy, it doesn't here. I'm just going to put them separately just to make things easier. These are at minus 12 eV. Right, and I'll just mark it so that this one is z, and this is x, and this is y. Right, and there, of course, there are 1 electron in each of them. And let me make sure I remember the right ordering here. Right. 2G, okay. So it turns out that in nitrogen, again, I don't know whether the Z or the X's or Y's are going to show up lower in energy in nitrogen. I just have to do experiment to figure it out. And it turns out in nitrogen, the PX and the PY, the pi orbitals form first. We form a pair of orbitals, right? These are the pi and pi star for X and Y. Okay. And then the Z's combine in kind of a strange way. I'll draw it with a different color. The Z kind of shows up slightly above in energy, the pi's. And then the antibonding orbital shows up just slightly above the pi star. Right, and these are the sigma star and the sigma bond for the p orbitals. And then we can just fill them up, right? This is the complete molecular orbital set. Right, we have combined 2 AOs to form 2 MOs for the 1s. Same for the 2s. We have 6 total atomic orbitals. In the p's, they form 6 molecular orbitals. Right, and we just fill them up from lowest energy to highest, right? So we're gonna get a fully filled pi shell. and then a fully filled sigma shell, right? That's completely bonding, fully bonding, right? No antibonding orbitals in the valence. All right, so now the question is, so this is the complete molecular orbital diagram for nitrogen. And let's just do some analysis, very simple analysis about the bond here. I said these two cancel each other out, right? The S's cancel out, right? Every bonding interaction we create, we delete with an anti-bonding interaction. No net bonding, no net bonding. Right? The electrons basically just cancel each other out in the molecule. Right? Because we have equal number of bonding and anti-bonding electrons. Right? But the P's are different. Right? In the P's, we have a fully filled bonding shell and nothing in the antibond. Right? These are pure bonding interactions. Right? These electrons combine to create bonds. Right? And how many electrons are there per bond? 2. Right? Pair electrons together for a bond. You could say, hey, this is 3 bonds. Right? There are 2 pi bonds and a sigma bond. Right? Well, that's a classic triple bond. Right? If you go back and think about acetylene, carbon triple bond, CC double bond, triple bond, right? You have a sigma bond that runs through the middle of them. And then the pi orbitals, the pi bonds, right? The double and the triple part of it lie along the x-axis and the y-axis like this. And that forms a triple bond, right? This is a classic triple bond. And there's a really easy way to calculate this, right? So we said that this is N2 is a triple bond. I should let me not use that symbol here. So again, the way we always draw this is like this, right? Lewis dot structure, right? Triple bond. And there are two pairs of electrons in the valence that we haven't accounted for. These are the lone pairs. Right? The 2s2, these electrons basically just sit on the atoms like this. 2 lone pairs here. Right. So in our case, these triple bonds, the triple bond comes from the 2p combinations. And these are the 2s2 electrons on the lone pairs. In reality, it's a little more complicated than that. So we have to hybridize the s's and the p's like we do in carbon. Right? We have hybrid orbitals that are combinations of s's and p's. That's maybe a better way to look at this. And that we actually have 4 somewhat. Nitrogen has 4 equivalent bonds effectively, but one of them is a lone pair. But it's the same interpretation. Right? We can use hybrid orbitals, and that gives us a little more insight, but the idea is exactly the same. Right? The bonding characteristic of nitrogen comes from the P's, and the lone pairs are largely of S character.
And what does that say for 2p?
2p combination. They're 2p they're from the 2p's. I'll just write 2p. Maybe that's just easier. Right, and of course, this explains precisely why nitrogen is such a boring molecule and so stable. Right, it's got a really, really strong bond. Right, because it has a completely filled valence bonding characteristic. Right, it has the best bond it can possibly have. All the electrons are combined in precisely the right way to maximize the strength of the bond. There are no bond, right? And so in order to break this bond, right, we either have to pull these electrons out of these really, really strong bonding orbitals, or we have to pump and ionize or remove or add electrons, right? We have to add electrons and ionize nitrogen and put new electrons in the antibonding orbitals to remove it, right? We would have to reduce it too, right? Right? Reduction of a species is literally taking an electron from one molecule and putting it into the first unoccupied molecular orbital of your molecule. That's what reduction is. Oxidation would be removing the lowest lying, the electron from the highest lying occupied orbital. Right? If I were to remove one of these electrons, that's oxidizing into, and reducing it would be donating an electron into one of these, right? But it takes a lot of, right? These orbitals are very high in post-ionization limit. These are not very stable places to put electrons. Nitrogen does not like to be reduced. Right? It also doesn't like to be oxidized because it takes a lot of energy to remove these electrons as well. Right? So an incident electron will be destabilized, and the current electrons in nitrogen are quite stable because they're in very strong bonding arrangements. So that's why nitrogen just sits around and does nothing. It's completely inert because the molecular orbitals are structured such that it's really hard to remove an electron. It's really hard to add one. There's not a lot of thermodynamics impetus to add an electron and to reduce nitrogen. Okay. The other thing is that the electrons are all paired, right? And what this would mean is that there's no net spin, right? There's no net electronic spin for nitrogen. So it's a spin singlet. And all the electrons are paired. What that means is, let me just write that down. Right? It's all electrons are paired. Call that a spin singlet. And spin singlet molecules have a very, very important property, or lack of property, not magnetic. Right? In order for an object to be magnetic, a molecule to be magnetic, it must have an unpaired electron in its valence orbitals. Right? So nitrogen is not magnetic at all. All right, you may say, okay, so what? Well, when we move to oxygen, we're going to see that things change a little. Right? This is something we may want to think about in these diatomics. This oxygen has a very, very different structure and very, very different properties. Even though the only difference between nitrogen and oxygen, we've added one electron to each atom. Well, we're going to see in just a minute that oxygen is very, very different. But what I want to show you now, we can kind of sit and let this marinate just a little bit while sorry, let me just move this over. Apologize. I'm not gonna change it. Let this marinate for just a second. I'm sorry, I didn't mean to close this. Screen is on its own. There we go. I want to show you an image. I get it. Up. Of how these orbitals, right? So the important part of the bonding in the second row that are these p orbitals, right? They ultimately determine the bonding characteristics of the molecule. Right. So one of the things is though, as you start to add more electrons into the valence of your atom, they start to repel each other, they start to shield each other. And therefore, the bonding characteristics of the Z versus the X and the Y start to change. And what that will do is cause the sigma orbital to be stabilized relative to the pi orbital, or vice versa. And so what happens is that the ordering of these molecular orbitals right here in the bonding region in particular change as you go across the periodic table. And again, this is not an obvious point. It's something that you can only really see with calculations and experiment. There's no way for me to a priori tell you this. I just know experimentally this is what happens. And of course, this is the framework for a calculation that you can do on a computer, which will also show you the same thing. Right? And this is just a qualitative approach to a real quantitative model. So what we see, so let's look, I gotta make a new slide here. Let me paste this picture here. So let's look at this picture. This is a correlation diagram between all the diatomics on the second row, right? Lithium all the way up to fluorine. We'll ignore the noble gases, of course. If they have fully filled valences, they don't make bonds. Right, so let's just look at our labels here, right? These are the bonding and anti-bonding orbitals for the two S's, right? So you can see once we hit beryllium, they're completely filled. Right, so lithium, dilithium, actually it has quite a strong bond in the gas phase. It's purely a single two bond between the two s orbitals, right? Lithium dilithium. You're a Star Trek fan, you've heard of dilithium, sure. Right, and then as when we go to beryllium, we fill that shell, right? And beryllium and Be2 is not a molecule, right? Because its 2s shell is completely filled. There's no net bonds. Right? And you can see as we get to diboron, interesting things start to happen. But notice these are the pxpy, the pi orbitals that form this pair right here. As you can see, as we go across the periodic table, the energy of them starts to decrease, right? And the reason why they start to decrease again is due to shielding, right? The px, the s, the two s orbitals start to become, as you can see, become deeper and deeper. They begin to shield the p valence more and more as the nucleus gets bigger and bigger, driving them deeper and deeper, which then more effectively shields the p orbitals, driving the p orbital energies down and down and down. Okay, but the most important thing is that the x and the y's, they're perpendicular to the core valence, the cores, right? The cores are all s orbitals, right? So the density lies along the bond. So the x and the y, the electrons in the p orbitals along x and y out of the plane of the bond, they don't really care that much. They're only mildly affected because they're generally pretty far out. Right? Remember, p orbitals, p electrons tend to be further away from the core than s electrons. But the pz electrons, they get much more effectively shielded by the core electrons because they also lie along the bond, right? So the shielding effects of the s orbitals mostly affects the electrons that lie along the bond axis. So therefore, the pz electrons tend to be more effectively shielded by the core than the px and py. So as you start to fill the valence up, go from dicarbon, which let me tell you is a very, very common molecule in the gas phase, not here on Earth, but literally everywhere else except for Earth. And as you go to nitrogen, oxygen, and fluorine, the 2pz bonding orbital decreases in energy significantly because they more effectively interact with the 2s orbital, shielding them, than the px and the py. And as you can see, when you go from nitrogen to oxygen, the ordering flips. Well, that's a bad color, sorry. Right, so this is the sigma 2pz, and this also is, and this also is. Right, so you can see that when you go from nitrogen to oxygen, right, the ordering changes, right? Because these orbitals interact with the 2s electrons fairly effectively. So what's happening is that these pz electrons, what actually happens here, and so let me just write this, as valence gets larger, as valence fills, the 2pz electrons, what we say, mix with the 2s electrons via shielding. Which selectively lowers the energy of the sigma bond between the 2pz orbitals. Right? What happens is that these p orbitals, what I mean by mix is that these orbitals here, these sigma orbitals that are formed, they have a little bit of s character in them. They share a little bit of the s and the p electrons and nitrogen share a little bit of density together, and they form orbitals together. I call this sp mixing. Again, not super important. The better way to think about this kind of classically or more simply is that these electrons are better shielded, and the more electrons you put into the valence, the deeper those electrons get stabilized, right? Because these electrons want to push away from the X and the Y's, and they want to be effectively shielded. And so they push away from the PX and the PY, which stabilizes them relative to the X and the Y. Okay, so there's this really interesting flip right here at oxygen. Really interesting flip. Right, so let's look at this oxygen valence really quickly. So let's look really quickly at oxygen. Again, we don't have to do, yeah, of course. Yeah. Well, you know what? I don't even need to draw. Let's just use this slide. And let me get my picture. Oh, maybe I don't. Here it is. Excellent. Okay. All right, so let's look at what happens in oxygen relative to nitrogen here. Right, we don't even need to draw anything. You can just use this correlation table. So again, the only difference between nitrogen and oxygen is that we've added 2 electrons. Well, of course, they're different atoms with a different number of protons, but in terms of the electronic structure, only 2 additional electrons, right? So let's look at how this builds, right? So unfortunately, remember in nitrogen, we've completely filled the bonding shell, right? These are the bonding orbitals of the P's. They're completely filled in nitrogen. So those 2 electrons in oxygen have to go into the next set of antibonding orbitals, which are these pi star orbitals right here. That's the antibonding orbitals. I'll draw that really quickly, right? So this is pi star. Right, so now there are, in oxygen, there are now 2 electrons in the antibonding orbital, which negates 2 of the electrons in the bonding orbitals. Right, we've broken half of these pi bonds. Right here we have 2 pi bonds. Now we still have 2 pi bonds, but we now have 2 electron equivalents in the pi antibonding. So we've canceled out one of the bonds. Right? And of course, that's not surprising, right? Because what's oxygen's bond? It's a double bond. In fact, right, oxygen is a double bond. Nitrogen is a triple bond. Of course, fluorine is a single bond. And of course, it has to be a single bond because look at the molecular orbital diagram for fluorine. The pi star is completely filled, right? We've canceled out all of the px and the py contributions in fluorine, right? So this double bond that forms from these pi orbitals are completely gone. So all that's left is this sigma bonding orbital here in fluorine. Therefore, we just have a single bond, right? You could take this to the logical conclusion now. What do you get in carbon? C2. This is a single, a double, a triple. What do you think C2 is? Turns out there's C2, it's kind of funky, but there is evidence to suggest that C2 has a quadruple bond. It turns out to be slightly weirder than that. Unfortunately, it's always more complicated. But there is evidence to suggest that carbon C2 has appreciable quadruple bond character. Right? Which is exactly what you would expect from the molecular orbital. It's very interesting. Right, but again, what I really want to focus on though is this oxygen. Oxygen is an intermediate condition because the pi orbitals now have unpaired electrons. Well, oxygen. Right. Remember when we in old school chemistry, general chemistry, how would you draw the Lewis dot structure of oxygen? Right. We always write oxygen like this, right? Lewis dot or Vesper, this old school crap that you learn in Gen Chem, right? You would always write oxygen with a double bond with 2 lone pairs on each oxygen, right? Right. What does this structure suggest to you? That all the electrons are paired, that this is a singlet. Right? You've got 4 electrons in the bond, you've got 4 sets of paired electrons. This should be a singlet, spin singlet from Vesper, but it's not. The ground state of oxygen says that there are 2 unpaired electrons in the system. So oxygen, Vesper predicts that oxygen is a singlet, has no spin, and therefore not magnetic. Let me just write that. This suggests spin singlet, right? Just like nitrogen, not magnetic. Right? But an experiment shows, and I'll show you an experiment in just a second. I'll pull up the video. Says that oxygen is a spin triplet, which means it has 2 unpaired electrons. So 2s plus 1 is equal to 3, and is magnetic. Oxygen is a magnet. And the reason why it's a magnet is entirely due to its molecular orbital structure. It has 2 unpaired electrons in its valence at 2 different orbitals. So Vesper gets this completely wrong. Right? And this, of course, is why oxygen is such an effective oxidant. Right? What is oxidation? Oxidation is, effective oxidizer. Excuse me. Effective oxidizer. Right? Because what would oxygen do if it oxidizes a molecule? Right? It's going to take another electron, right? And it's going to stick an electron and pair one of these. Right? So if I oxidize oxygen, or if I use oxygen and I reduce oxygen by oxidizing another material, that reduced electron is going to come into here and cause a pairing. And pairing electrons is always stabilizing. Once you have a half-filled shell, there's actually quite a bit of energetic impetus to pair one of them, right? The electrons will always fill one by one, but once you have a fully filled shell, pairing actually provides quite a bit of stabilization. So oxygen is a very effective oxidizer for this reason, because it's got 2 slots for electrons that it wants to fill. Oxygen wants to break this bond. Oxygen would be more than happy to fill this bond, because then it'll pair those electrons and they don't repel each other. Right? So oxygen, that's why oxygen is so reactive, because there's a really, really nice place to add those electrons. Right? Stick it right there. That's why oxygen is such an effective molecule for combustion, and you can't combust with nitrogen because there's nowhere to put electrons in nitrogen. But in oxygen there is. And solely due to this fact. Right? So Lewis dot and Vesper structures are inherently incorrect. They don't have any, the only thing they provide you is that it's linear, which is true. But of course, 2 atoms are always linear because 2 points form a line. It doesn't really tell us anything. But this is actually a very, very incorrect model for oxygen. This actually reflects singlet oxygen, which is a higher energy state of oxygen. In order to go from triplet oxygen to singlet oxygen, you have to heat oxygen to like 1500 Celsius or maybe even higher than that. All right, singlet oxygen, where this electron and this electron are opposite spins. Right? Flipping that electron requires significant heat and significant energy. And that's the structure you would get for singlet. Actually, oxygen is what we call a diradical. It's got 2 unpaired radical-free radical electrons. But I don't want to give Gilbert Lewis and Linus Pauling too hard of a Robert Mulliken too hard of a time. They didn't understand molecular orbitals when Vesper theory was invented. This was invented decades after Lewis dot structure was. It's just unfortunate that we teach it, right? Right, so I want to show you a proof that it's magnetic. Maybe you guys have seen this experiment, maybe you haven't. My high school chemistry teacher did this for me, or for us in class. But again, you can't really tell oxygen is magnetic in the gas phase because, well, actually you can. If you put a magnetometer in front of a fairly pressurized canister of oxygen, then you can measure the magnetic field of it. But it's better to see oxygen in condensed form as a magnet, so you can liquefy it. And if you put, there's two different ways to do this experiment. This is the way I didn't see it, but it works just as well. If you liquefy oxygen and put it in front of a magnetic, so say for instance, you have a puddle of liquid oxygen, right? And then you take a magnet, a permanent magnet, a little neodymium magnet or something, and place it in that on top of that liquid puddle, liquid oxygen, it floats, it levitates because it repels. Right? And so in this instance, we're doing the opposite effect. He's going to take liquid nitrogen and put it on a permanent magnetic surface. And what you're going to see is the bubbles, the nucleation of the liquid, it doesn't spread like a liquid because there's a magnetic force repelling it. And I'll just show you what it looks like. Let me just kind of go back a bit. And you can see the little, once it goes, here. You can see the little dot, the little beads of liquid oxygen dancing around the magnetic surface, right? Now, the surface tension of the liquid of liquid oxygen is increased because the magnetic field is repelling the liquid oxygen, forcing it to form these tight little beads, right? It actually adds to the surface tension, the magnetic field. There's an additional force compressing the liquid oxygen on top of this magnet, right? And that's because the material is magnetic and it repels the magnet. Right? You wouldn't get this from Vesper theory, right? You can only understand this through molecular orbital theory. It's the only way to understand this. Has anyone ever seen this experiment before? Has anyone ever done this? We should do this in PChem lab. It's kind of hard to make liquid oxygen, unfortunately. That's the only problem. You have to have a good cryostat to do it. But it's not too hard to make. Yeah, it's beautiful, isn't it? I think it's really cool. I couldn't find one of the opposite. It's really cool, but if you make a little puddle, if you buy a little like puddle magnet, it will float. It'll levitate on top of the material. You can get it to rotate and orbit like a gyroscope on top of it. It's really cool. And you can see them dancing there. Yeah, maybe I'll do that experiment next year. Okay. All right, so I'm going to say that's about all I want to say about diatomics today. There's really not much more to add. Of course, we can go into the D block and start thinking about d orbitals, but the analysis is exactly the same. You just pair d orbitals based on their alignment to each other, and if you took inorganic chemistry, you would have learned this is what's called crystal field theory or ligand field theory. That's what the inorganic chemists call this, the molecular orbital theory of the D block. Right, but the principles are precisely the same. Okay, what I want to close out with today is two more examples. Well, maybe only one. We'll see what happens. I want to look, right now what we've only looked at are homonuclear diatomics. Right? Each atom is the same, right? So what we haven't considered is, what if we pair two atoms together that aren't the same? A heteronuclear diatomic. Right, there's not that many of those, but there are a couple of important ones. OH is a great example, hydroxyl radical. But the example I'm going to show you is a little different. I think it's a really nice analysis. Right, we often talk about this idea of electronegativity. Right? And if you go look at your periodic table or something, right, electronegativity is tabulated based on the atoms. Right? Fluorine has electronegativity, nitrogen has its own, hydrogen has its own. Where does that number come from? And the fact of the matter is that electronegativity is not a meaningful number when the atom is by itself. Right? If an atom is by itself, it's just a sphere. It's not, there's nothing that makes it electronegative. It has to be in the presence of something else, where you have an asymmetry of charge, right? Something's more negative than the other thing. Right? So electronegativity only appears in the context of having at least two atoms. And these numbers that you read about electronegativity come from our understanding of how electronegative atoms bond with non-electronegative atoms. It's a product of an empirical measurement of how electrons are polarized in a bond when two different atoms combine. It only exists in the context of bonding. Well, or any sort of interatomic interaction. Maybe not a bond necessarily. You can have two atoms close together that aren't bonding, that where it might affect things, but regardless, electronegativity means two objects for it to be defined. So I want to look at this from the context of a bond. Right? How does electronegativity show itself in molecular orbital theory? All right, so the example I want to look at is NH. Right? The ammonium, I don't know if you call this the amino radical. I forget what this is called. Anyway, it's a very, very simple molecule. And I'm curious about what the bond of NH is. Of course, we expect this, right? What is it like in ammonia, right? Remember in NH3, the NH bond is a single bond. Okay, so there might be a single bond between this N and H, and that should make sense, right? Because the hydrogen only contributes one electron. So probably the nitrogen also contributes one electron to that bond, therefore makes a single bond. Well, that makes sense. But we don't know, what about the other electrons, right? Where do they go? So the best way to think about this is to think about where the energies of each of the atomic orbitals lie. Right? We did that before. Remember, so let's think about H. The 1s1 is at minus 13.6 eV. Right? And I'm just going to also add the 2s0. This is at minus 3.4 eV. Right? Even though there are no electrons in the 2s orbital, maybe it's closer to the nitrogen orbitals than the 1s, and maybe it'll play a role. We'll see. And then the only ones, remember, we only combine orbitals that are close in energy to each other, right? We can go back into our notes to nitrogen, and there's really only one set of orbitals for nitrogen that are close to hydrogens, which are the 2p's. Right? The 2p3 is at minus 12 eV. Right, so the combination that we expect from MO theory to form a bond, right, the most likely combination, the most likely bonding combination could be the 1s1 in the hydrogen atom plus the nitrogen 2p3. Right, because the two S's are probably a little too far up in height, right? We're not going to have a 2s, 2p combination probably. And we're not going to have the two S's from nitrogen come and make, because they're closer to like minus 20. They're kind of far away. All right, so the only combination that's going to happen is between this orbital and this orbital. So let's put these on a nice little plot. Let's draw our diagram. Right, and I'm going to be a little dramatic here. So we'll set this to be minus 3.4. This is where the 2s is for hydrogen. This is the hydrogen side. I'll put hydrogen here, N over here, and NH in the middle. And this is the 2s. And then way down at the bottom, there's something down here like minus 13.6. And that's the 1s1 orbital for hydrogen. one electron in it. And then the nitrogen 2p's, which of course there are 3 of them. Somewhere like over here. 3. This is the 2p3. And this is that minus 12. All right. Anyway, very dramatic combination here, but or order scale, but that's okay. Okay. All right. So now the question, of course, is how do these two combine? All right. We've only considered how p's combine. But how does the s and the hydrogen combine with the p orbitals? Right? Does it combine differently with the x and the y than it does with the z? Well, you better believe it, right? Because the z's along the axis, the bond axis, like the s orbital is, and the x and y's are perpendicular off the bond axis. So they might be different. So let's look at that. All right, let's do the easy one first. All right, we'll take the 2pz, nitrogen 2pz, plus the 1s for hydrogen. Let me just kind of demarcate this on the side. Right, so here's my little bond between them. Here's my hydrogen orbital. It's got some sign. Say this is the positive sign for the wave function. And then we've got a p orbital over here. Blue. Along the z-axis. And we, of course, we have one sign this way and another sign on the other lobe. Right? It should be easy to see that these combine nicely. Right? We have like combined with like. They overlap nicely. They have the same symmetry. Right? We basically kind of have a spherical thing adding to another sphere. These should add very nicely. We get bonding. Right? So we get a sigma orbital, which looks something like this. We get this nice bonding contribution across the bond and a little negative lobe over here. Like that. And then we have sigma star bond, the anti-bonding combination, which instead looks, let's see if I can get this good. Oh, sorry, that's not supposed to be a circle. It automatically created it as a circle. There we go. That's what I want. A little p lobe there. Here's the bond. I want to get smaller. Right, and it's got a nice note in it. Okay, so the PZ and the 1S will bond with each other. Okay, so we at least get one bonding combination between the two atoms. All right, but what about the X and the Y? Well, we only have to look at one because they're equivalent. They're just rotated 90 degrees. So let's just look at 2px for the nitrogen plus 1s for the hydrogen. Bond axis. Here's my hydrogen orbital. And then my p orbital is aligned perpendicular like this. Now, when we add these together, let's use a little bit of symmetry. Right? When we add them together, we get a bonding combination, a constructive combination north of the bond between this lobe and this lobe. They're matched. Right? So we get constructive interaction here. But look on the other side. We get equal and opposite destructive interaction on this side. Right, this is the negative. Right, so I'll just cross that. Right, this is the negative, right? This is this is a destructive interference between the wave functions. And this is constructive on the north side, right? So we get equal and opposite effects north and south of the bond. They cancel out. Right? All the positive overlap we get here, we get equal and opposite negative overlap on the other side.
That's supposed to be +1 H. The words, yeah,
Plus one S in the H atom.
oh, okay.
No net bonding. Right? These don't interact. The px orbital and the py orbital do not constructively overlap with the 1s orbital of hydrogen, because the symmetry of the sphere and the symmetry of the lobe-like structure of the p orbital leads to an equal and opposite effect on each side of the bond. So we call this not a bonding or an anti-bonding interaction. This is what's called a non-bonding interaction. Nothing happens. Okay. So that means that the Z and the 1s are the only thing that forms a bonding anti-bonding pair, and the X and the Y orbitals of the nitrogen just don't do anything. All right, so when we construct the orbitals for NH, we can draw a very, very simple line here, straight across, where we put our two p orbitals, our X and Y, right? There are non-bonding p orbitals. Right? They don't change in energy. They have no hydrogen characteristic. They're not interacting. They're just nitrogen electrons. No bonding. You just move them over. All right, but we do get a combination between the 1s and the Z. All right, and so when you get a bonding combination, you form an anti-bonding orbital that's slightly higher in energy and a bonding orbital that's slightly lower in energy. So we'll form a bonding orbital over here and an anti-bonding orbital up here, like this. And this comes from the PZs, right? This is our sigma star and our sigma. All right, so let's fill the electrons. We've already put 2 in the middle and we have 2 left. So the last 2 electrons go into sigma orbital. All right, so what does this tell us about the bond, about the system, nitrogen, this radical? Well, it's obviously a radical, right? Because we're left with 2 unpaired electrons. It's a diradical, it's a spin trip. It's like oxygen. And there's a single bond, right? We have 1 net bonding interaction. Right? So the way we would draw this with, Vesper theory would be NH. N has a lone pair from its 2s. These are the 2s. 2. And then there are 2 additional unpaired electrons here and here, which have px and py characteristics. Right, so this is a diradical or a biradical, called diradical, with a single bond. Now here's the interesting thing. Look at electronegativities, you think, oh, hey, when I have a nitrogen and a hydrogen, that's an electronegative bond directed towards the nitrogen, right? That's what we always say, right? The nitrogen is polarized negative. And of course, that's reasonable, right? Because it's got a lone pair here and 2 unpaired electrons, right? It's got a lot of negative charge over here. But what about the bond itself, right? As I just said, these electrons don't have anything to do with the bond. Right? They're in completely different orbitals. They're completely uninteracting with the bond. Right? The only electrons that contribute to the bond is this electron in the hydrogen and this electron in the 2pz orbital. And where do they go? They go into an orbital that's hydrogen-like, right? This energy of this bonding orbital is hydrogen-like, right? Because it's close to the energy of hydrogen. And this one up here is nitrogen. Right, so these electrons are in an orbital that's closer in energy and has more hydrogen character than it does nitrogen. Right? This orbital is very far away from this. This electron's been taken very far away in energy, and it's brought into an orbital that's closer in energy to hydrogen. This bond in particular is not polarized towards nitrogen, it's polarized towards hydrogen. These electrons are stored in an orbital that's mostly like hydrogen, right? Because it's closer. So these are hydrogen-like electrons. The hydrogen actually pulls those electrons away from the nitrogen. So from the perspective of the bond, the hydrogen looks electronegative, contrary to what we would expect. Right? So we would often say that these are polarized towards hydrogen. And then if we were to put electrons in this antibonding orbital, they would reside closer to the nitrogen. Right? This is a nitrogen polarized orbital. All right, so electronegativity is a very, very sensitive topic. Maybe that's not the right way to say it, but it's context sensitive. Right? When we talk about electrons as a whole, well, N is clearly electronegative, right? It's got two radicals, it's got a lone pair, it's got a lot of electrons around it, right? But in terms of the bond itself, the characteristics of the bond, imagine what I do now is I take that bond and I pull it apart, right? A homolytic cleavage of the bond, not ionization, nothing. I'm just going to stretch that bond until it breaks. What would it break into? Well, right, when this breaks homolytically, those nitrogens, those hydrogens, those electrons are closer to the hydrogen. So the predominant pathway for breakage along this axis, without exciting electrons, so homolytic cleavage, which means breaking the bond without ionizing it.
Wait, what does it say? What cleavage?
Homolytic.
Oh.
Right, so we're just breaking, we're not ionizing the bond, we're breaking the bond. All right, let me just get rid of homolytic, actually. This is called cleavage, right? We're going to pull the bond apart. What would it pull apart to? Well, those electrons are stored near the hydrogen. So what you're going to end up getting is N plus a hydride ion. That hydrogen is very basic in that system as you pull it apart, right? From the bond's perspective, the hydrogen is the electronegative element. This is a polarized hydrogen bond. It's a hydride, not a proton, but a hydride. It's a basic proton, not an acidic proton. Right? And the sole reason why that is because of the way that the bonding structure works. So when you add two orbitals of very different energy, very, very different, you're going to have polarization of the electrons in the MOs. And they're going to be polarized towards the atoms that are closest in energy. In this case, as I said before, bonding electrons are polarized towards the hydrogen because they're closer in energy. This orbital has more hydrogen character than nitrogen. And this one has more nitrogen character than hydrogen. So therefore, when this breaks apart, most of the result that you're going to get is hydride. It's a basic ion. Right? Again, you wouldn't expect that from just regular electronegativity. You would think, well, electronegativity, when you break it apart, you're going to get N minus. Right? It's going to take those electrons, which is electronegative. That's not what happens. Break this apart, they go to the hydrogen step. Right? And you wouldn't know that unless you drew the molecular orbitals out. Right? Molecular orbitals determine the bonding, they determine the chemistry. Not electronegativity and low atomic properties, they guide you, but only so much. ultimately you have to think about how the orbitals connect. And what does the bond actually look like from the perspective of the electrons? And as you can see, it really, really depends. It's a very careful, subtle problem. And so again, these are very, very simple examples. Okay? When we go and we want to do it for more complicated things, we have to use the computer to do it. But all a computer does is precisely, for most calculations, especially for small molecules, gas phase molecules, liquids, we make this approximation. We say, hey, we start with some atoms with some atomic orbitals. We combine them together. Very simple way. We make some corrections, but ultimately, all the computer is doing is building these molecular orbitals for you with a higher precision and quantitative precision. Right? And the computer will teach you again that this happens contrary to what you would expect from general chemistry principles. Right? And again, this is the important thing about modern chemistry, right? The things that you learn in Gen Chem, there's nothing wrong with them. But a lot of them were designed before people understood how molecules work. So much of chemistry is empirical. And let me see how I want to say this. Rules that we come up with explain chemistry to a certain framework, a certain understanding. There's always a level deeper. But there's ultimately a level, you're always approaching the exact answer, right? So eventually there's not like everything is ultimately wrong. There's always a new way to approach things. You'll eventually get the right answer. All of this proves that, right? I can show you, if we had time, that taking this approach to the logical conclusion should give you the right answer about the molecule. Right? We can solve the Schrodinger equation in theory with this approach. It's not that hard. It takes a lot of calculations. Might take a lot of time on the computer to do it, and the calculations can be massive. But the theory is all there. You can build those calculations, and you get the right answer for the right reason. When we talk about Vesper, and we talk about Lewis dot structure, and we talk about things like that, electronegativity, these are simple rules of thumb. Okay? But as you can see, it depends on the context how you apply those rules of thumb. Okay? Nitrogen is typically more electronegative than hydrogen. Nothing wrong with that. It's exactly correct, right? HCl, for instance, right? HCl forms Cl minus and H plus, right? You know that. But this is a situation where that doesn't happen, right? And that only depends not on the electronegativities of the atoms, but the way that they combine together. Right? And you can only know the truth if you know exactly how things combine and how they polarize, and you know the context of your molecule, right? And computers can solve that for us. Sticking around for +1 after this, or if you're taking your senior in the +1 program, you're going to take Comp Chem with Dr. Zhao, you'll learn these concepts. Okay? Everything after 1940, right? 1940, we hit this problem. I'm just about done. And they said, hey, the only way we can move forward is computers. And so ever since then, we've just been working on computers and using computers to make our predictions better and better and better. And what computers show you is that this gets the right answer for the right reasons. It's the first approximation that's correct, almost universally. It gets you the right answer for the right reason. It's not necessarily quantitative, right? As I've shown you, right? You can't predict anything numbers here, but we can predict the right behaviors, and we can construct the right framework to understand the chemistry for the right reasons. Okay, that's all I have to say today. Thank you all for your hard work this semester. We got one more problem set. Thank you all. Some of you I'll see next year. Some of you I may never see again. Some of you I won't be able to get rid of. But I appreciate your attendance and your hard work regardless, and good luck in the future. Thank you all.
Is that yours?
What?
Oh, no.
Yes, it is.
Oh, it is?
Yes. What? Because there's a kitty on it makes you think it's not mine?
Well, it was a wristlet, so I just.
Oh, yeah. Well, it was my wife's at one point. My wife's name is Kitty, so I have a lot of kitty people better than me.
Oh.
My bad. Hi, what's up? Oh, that's fine. I'll grade them this weekend. All right, thanks, Ashley.
For the past 15 years of my life, I can't read.
Anyway, I can't read it.
Yeah.
Yeah, so there's no reason to go,
What's up?
You're going into this what?
Yes, I have to be where everybody.
Yeah, give me a couple days. I need to talk about it on Friday and then figure it out. Can you say-
Like, what about-
I under-
was gonna say, I don't
Uh,
know, like,
let me-
I went there.
96.
Let me talk.
I don't think she's-
You're already doing research. 3 credits of research, I presume, with Dr. Sark.
Well, I'm not doing the next one.
is speaking
Oh.
some?
Oh,
I do.
okay.
From which
Um,
one?
Either way, I can't.
I'll have to double check. We might be able to set something up and put it in as 2 credits of research.
I can't drive.
Which again, doesn't matter, just basically. Let me make sure that that's okay first, okay? And I'll get back to you.
That's my
All right,
favorite.
you're welcome.
You're gonna be in 311, right?
I just got another package email.
Yeah, I'll be in 311 for like 2 more hours.
Because, yeah, got it.
Yeah, we'll just try and make this as quick as possible.
Okay. I know I have some crises to solve on the instrument, but they shouldn't take that long, and then I'll be able to help you. Sean might be up there too right now.
Bonds? Yeah, but I'm going to FSA first, so I'm not gonna get there till
I don't
6.
know how long it'll take.
I have a quick question.
Yeah, what's up, Ellen?
Do you read all of the PChem lab, like course evals, or just the ones for your section?
I would like to, but I don't think I
I-
don't-
there's
won't
a
be able to
lot.
see Sorveshes.
Okay, okay,
I think the chair will read them.
okay, perfect.
I may be able to read them myself, but otherwise, if you have. I know they're not anonymous. You can always email me your if you have something you
Okay.
want to say about that class that you think I should know about, just email me. I
Okay.
won't share your name with anybody.
Okay.
I won't retaliate against you.
I
That's up to
appreciate
you.
that.
You're welcome.
Perfect, thank you. I just have a quick,
I'm also at the forensics honors